Good afternoon, everyone. For today, we are going to discuss about the hyperbolic functions. For our learning objectives, at the end of the lesson, we should be able to define hyperbolic functions, identify identities involving hyperbolic functions, and apply the formulas for derivatives and integrals of hyperbolic functions. As an ordinary trigonometric function is defined on a circle, similarly, hyperbolic function is defined for a hyperbola. The forms of hyperbolic functions or hyperbolic trigonometric functions may appear new, but their properties are concepts and functions we've already encountered in the past. Hyperbolic functions are defined in mathematics in a way similar to trigonometric functions. As the name suggests, the graph of a hyperbolic function represents a rectangular hyperbola, and its formula can often be seen in the formulas of a hyperbola. Johann Heinrich Lambert, a Swiss-German mathematician and colleague of Euler, is the first person to publish a comprehensive study on hyperbolic functions. One physical application of hyperbolic functions involves hanging cables. If a cable of uniform density is suspended between two supports without any load other than its own weight, the cable forms a curve, what we call a catenary. High voltage power lines, chains hanging between two posts, and strands of a spider web all form catenaries. The following figure here shows chains that is hanging from a row of posts. Chains between these posts take the shape of a catenary. Hyperbolic functions parameterize a hyperbola the same way trigonometric functions parameterize a circle. What makes these functions even more special is that they can be expressed in terms of exponential functions. So, how do hyperbolic functions relate to hyperbola? Let's take note that hyperbolic functions are defined through the algebraic expressions that include the exponential function e to the x. Well, let's take a look at hyperbolic sine of x. Hyperbolic sine x is equal to e to the x minus e to the negative x all over 2. Now, what does this mean graphically? Let's try to break up this expression into two terms. Here, we are going to have e to the x over 2 minus e to the negative x over 2. If we will graph these two terms, we will get a hyperbola. And the sum of these two curves at every point will give us hyperbolic sine, which we can see here crossing the origin and then getting closer and closer to either sections as we go to positive and negative infinity. The domain and range are both all real numbers. Next is the hyperbolic cosine x. That will be the same as hyperbolic sine. As you can see, the operation used in here just switched from subtraction to addition. That means that the part of the hyperbola that was below the x-axis is now above it. And if we add up these curves, we get hyperbolic cosine. Hyperbolic cosine has a domain of all real numbers, but the range will be from 1 to positive infinity. Hyperbolic tangent will just be hyperbolic sine over hyperbolic cosine, and that will look like this, with horizontal asymptotes at -1 and 1. And then, we can have the other three hyperbolic functions of cosecant, secant, and cotangent, which are just the reciprocals of the first three. Many of the trigonometric identities have corresponding hyperbolic identities. For instance, let's try to prove hyperbolic cosine squared x minus hyperbolic sine squared x is equal to 1. We will go back to our definition of hyperbolic function. Hyperbolic cosine is equal to e to the x plus e to the negative x all over 2. And this is squared, so our definition will also be squared. Minus the definition of hyperbolic sine, and that is e to the x minus e to the negative x all over 2. Simplifying our first term, we will get e to the power of 2x plus 2 plus e to the power of negative 2x all over 4 minus the squared of the second term also. So we have to simplify it again for us to get e to the power of 2x minus 2 plus e to the power of negative 2x all over 4. Solving our expression here, we are going to have 4 over 4 or 1. So this proves that hyperbolic cosine squared x minus hyperbolic sine squared x is equal to 1. Because the hyperbolic functions are written in terms of e to the x and e to the negative x, we can easily derive rules for their derivatives. The next theorem lists these derivatives with the corresponding integration rules. Our theorem deals with the derivatives and corresponding integrals of the hyperbolic function. There are 6 derivative formulas. So for example, the derivative of hyperbolic sine of u is the hyperbolic cosine of u times u prime. And the derivative of hyperbolic cosine of u is the hyperbolic sine of u times u prime. The third one will look familiar also. The derivative of hyperbolic tangent is nothing more than the hyperbolic secant squared times u prime. And there are 3 more formulas very similar to the corresponding trigonometric formulas. Now, let's try to prove a couple of these formulas. How about the derivative of hyperbolic sine of x? Let's define hyperbolic sine, and that is e to the x minus e to the negative x all over 2. So we need to have the derivative of that quotient, and that is e to the x plus e to the negative x all over 2, which of course leads us to hyperbolic cosine x. How about the hyperbolic tangent? What's its derivative? Well, hyperbolic tangent is hyperbolic sine divided by hyperbolic cosine, just like with the regular trigonometry. Now, we apply the quotient rule. So, in the numerator, we are going to have hyperbolic cosine squared minus hyperbolic sine squared, and by fundamental identity of hyperbolic functions, that numerator is nothing more than 1, divided by hyperbolic cosine squared, which of course can be written as hyperbolic secant squared. Now that we are done proving couple of these derivatives, let's now go to the integral of these hyperbolic functions. Remember that the derivative of hyperbolic sine u is hyperbolic cosine u times u prime. So that means if we have to integrate hyperbolic cosine u with respect to u, it will give us hyperbolic sine u plus that constant of integration c. Next one is the derivative of hyperbolic cosine u, and that is hyperbolic sine u times u prime. Integrating this hyperbolic sine u with respect to u, we are going to get hyperbolic cosine u plus that constant of integration c. Another is the derivative of hyperbolic tangent u times u prime is hyperbolic secant squared times u prime. So that means if we have to integrate this, it will give us hyperbolic tangent u plus c. So these are the derivatives and integrals of hyperbolic functions. Let's go now to our examples. In this problem, we are going to integrate hyperbolic cosine of 4x with respect to x. So recall that if you just have to integrate hyperbolic cosine, you will get hyperbolic sine of x, because the derivative of hyperbolic sine is hyperbolic cosine. But in our example, we have 4x, that is why we have to make a u substitution. So let u be equal to 4x. Now we compute for the du, and du is the derivative of u. In our example, the derivative of 4x is equal to 4. So we get du is equal to 4x. We divide both sides by 4, so we can write this as 1/4 du is equal to dx. Now that we have this, we are now going to substitute this into our integral. So we have integral of hyperbolic cosine of u 1/4 du. we can factor this 4 out. So it's 1/4 integral of hyperbolic cosine u du. When we integrate hyperbolic cosine, we will get hyperbolic sine. So, in this case, we are going to get 1/4 hyperbolic sine of u, and don't forget our constant plus c. Last thing to do is to replace our u with 4x. So, we are going to get 1/4 hyperbolic sine of 4x plus c. And that will be our final answer. For our second example, we are going to have integral of hyperbolic sine times quantity 1 minus 2x dx. Same process with example number 1, we are going to make a u substitution. Let u be equal to quantity 1 minus 2x, and our du will be equal to negative 1/2 dx. Since we already have our u and du, let's start to integrate. This will be now equal to integral of hyperbolic sine u minus 1/2 du. Putting the constant outside the integration symbol, we are going to have negative 1/2 integral of hyperbolic sine u du. And as we remember, the integral of hyperbolic sine u du is equal to hyperbolic cosine u plus c. So this will give us negative 1/2 hyperbolic cosine u plus c. We have to substitute our u, and that is quantity 1 minus 2x, and our final answer will be negative 1/2 hyperbolic cosine quantity 1 minus 2x plus c. For our next example, we are going to have integral of e raised to 2x hyperbolic sine x dx. We are going to pick up on the definition of hyperbolic sine x, which we should know is e to the x minus e to the negative x all over 2. Let's substitute that, and our integral becomes this one. Now, let's put our constant outside and expand our e raised to 2x times e to the x minus e to the negative x. Doing that, it will give us 1/2 integral of e raised to 3x minus e to the x dx. Integrating our e raised to 3x, well, that's going to be 3x over 3. And the integral of e raised to x is just going to be e raised to the x. So we should have that result in our concept of integration c. Let us put our 3 outside, which will give us 1 over 6 e raised to 3x minus 3 e to the x plus c. As we can see, we can still factor out e to the x, which is their common factor, and then our final answer will be this one. E to the x over 6 times quantity e raised to 2x minus 3 plus c. For our next example, which is our example number 4, as you can see, we have hyperbolic cosine of 4x. With this, we are going to have the definition of hyperbolic sine, but we will replace the x with 4x. By doing that, we get this integral here. Just like what we did in our example number 3, we will put our constant outside the integration symbol. After doing that, we're going to get half the integral of e raised to 7x plus e raised to negative x. Then we can integrate both those two terms so we can come up with this. And then simplifying our answer, we will come up with 1 over 14 times quantity e raised to 7x minus 7 e to the negative x plus c.